thank you everyone for being here and coming to the workshop that we've really wanted to organize. Now, I'm really excited about what machine learning could do in the medical domain, and obviously I won't be able to answer all of the questions that you might have about machine learning, but my hope is that I will give you enough information that will inspire you to inquire about this topic further on your own, because ultimately what matters is whenever the domain experts have the right tools under their hands. And it's ultimately up to those people who will use these tools in a proper way and will make a significant impact. So that's why we really wanted to have this workshop. Now, briefly about myself and Catherine, who helped me to prepare these slides. And I'm a PhD student here at Warwick as part of Tissue Image Analytics Labs, and recently also part of Warwick Machine Learning Group, where there's sort of more general machine learning research. Now, Catherine is a pathologist trainee, so I think this is really cool. We are sort of both young and new in this field, and this is our sort of attempt to inspire other people to inquire about this. Now, my real motivation about having this workshop was that last year when I went to ECDP, I was talking to some of the medical students who had their posters on their research that they've conducted, and in their research they were using machine learning tools developed by company X. And when I started asking these students, how did you use this algorithm? How did it work? These students told me, well, actually it didn't work at all on our data. We had to retrain it and then apply it to our data, which is a real thing, and this is something that we should be really thinking about when using these tools. And there are multiple other assumptions that we need to think about when using these tools. So we want to know what you think. We want to know how important you think this is. So please take our free question survey, which will help us maybe make something more about this and educate clinicians more about machine learning and statistical tools that we have, or people have in general. Now, in general, in machine learning, there are many type of tasks that we can solve, but the most common ones that we are solving within medical domain and pathology specifically is classification and regression. Now, the white circles and white diamonds are the data points, and in classification we just try to separate these two categories by a line, and that's all classification does. And in regression, we just try to fit the best fitting line that describes some sort of process that we see in the data, which is just this wiggly line. Now, our model in machine learning is the line itself, and we try to find the best possible model. So, for example, we could do it in the categorization of malignant versus healthy tissue, or we can do it for survival prediction. Now, in general, this is the only formula you will see in this whole presentation. Your data will be your X. This is the features or some sort of covariates that describe your data in the best possible way. Now, your second stage of the model development, of the machine learning development, will be the model, which is your F function, which you are trying to learn. And then the prediction that we are trying to do, which is, again, categorizing which category we are belonging to, the data belongs to, or predicting the survival. And that is really all there is to machine learning. And that's it, job done. So this is really an outline of what I'm going to cover. So first, we'll talk about data, which is really the key to any machine learning problem. You can have the best possible model out there possible, but if you don't have good enough data, there is nothing you can do. So we'll talk about how can we extract features from an image, and then some biases to keep in mind in pathology about that. And also we'll talk about the model. How does the model learn? What does it mean? And what are the implications about the learning for us? And then it will also be a bonus of additional resources, because there is not enough time to cover it all. But I hope I'll inspire you to look into those resources. Now, the data. Now, we have an abundance of data, and at the same time, not so much data in every individual lab, because we need annotations, and that is quite, takes a lot of effort to collect. But mostly, it's all images that we're working with. So I will focus only on images, but it generally applies to all sorts of data. So for machine learning model, it doesn't really make much difference between the image on the left and the image on the right. But however, for human it does. So for example, when a pathologist looks at the image on the left, you straight away recognize that there are red blood cells and there are lymphocytes there, and you are able, given your knowledge that you have already about the task, about the problem, and about the image, straight away derive some sort of semantic interpretation about what you see in the image. And also the same applies to the mushroom on the right. Now, it is much harder for the model to do that, to extract some sort of semantic interpretation about the image that it's looking at. This is really the task that we always try to solve within machine learning, within statistics, is how we derive the best possible features, the visual information about the image that we're looking at, such that we get as close as possible to the semantic interpretation of a human about that same data. So the question is, how can we extract visual information from raw data such that we get as close as possible to human semantic interpretation with the model semantic interpretation? So this is essentially the problem. Extract visual features from an image such that model semantic interpretation is as close as possible to how human would interpret the image. So let's talk about how we do that. So this is a mushroom. And we will focus only on a mushroom for now, because you've heard enough about pathology today. And this is just the same image for an algorithm as an image of as a pathology image. And it requires exactly the same techniques to process it. Now, this is also a mushroom, and you still can understand that. Now, generally, image is stored in 3 channels, red, green, and blue. Which makes it an array where you'll have for each pixel 3 numbers, which corresponds to how much color you have within that particular pixel. And this is also a mushroom, but now represented as an array. And on this array of numbers, we can perform certain mathematical operations that would allow us to extract visual features from an image. And this is essentially what we do. For example, we can apply simple mathematical operations such as thresholding and then get the boundaries of the mushroom. And then feed that into machine learning model, the most simplest one, and then be able to classify, for example, dogs versus the mushrooms, for example. Now, you can also convolve it with different filters, and you don't necessarily need to know at this point what does convolution mean. All you need to know is that, for example, there is by convolving with a certain filter, you can detect edges within an image. And this is an illustration of that here. You can't really see it very well on the slides in front of you, but if you could, you would have seen an outline of a mushroom. And note on deep learning applies this convolution operation of detecting edges or any other sort of features within an image automatically. And it applies many of them in parallel. And moreover, it learns what these features are, or it learns to extract these features from an image. So what you see here on the right is all possible filters that machine learning models, such as convolutional neural network, would apply to the image to extract visual information from it. So all of these sort of vertical, horizontal lines in there, as well as color variation, these are the filters that machine learning model has learned in order to be able to classify a natural imaging data set. Classify dogs versus turtle versus airplane, and so on and so forth. Any questions up to this point or concerns? No? Okay. So what are these filters? So like I said again, some of them will detect an edge which is horizontal, some of them will detect an edge which is vertical, and as you go up the complexity of the model, it might learn more and more sophisticated filters that would detect different variations within an image. So then, once we have these visual features that we extracted using the filters or whatever mathematical operation we came up with, and we get our diamonds and circles, then we feed it into our function, which is the f, the line, and we optimize the model to find the best fitting line, just a standard linear regression, to get the best possible prediction. And this is all there is to machine learning. So we're slowly getting into the section of the model, the meaty part. So we optimize the model to be good in prediction, and that model could be really anything. It could be, for example, a decision tree, which is something that we generally do every day. For example, if we try to predict if there's going to be a rain or no. or some other weather condition. So we will check through the window, is it sunny, is it overcast, is it rain? Then yes, prediction that it's obviously going to rain, and so on and so forth. Now, in terms of deep learning, where deep learning really came in since 2012, is that it allowed us to step away from deriving the optimal features from the image. We don't need to extract visual information anymore, or at least that's what we think. Because our deep learning model learns these filters on the left that allow us to extract features from the raw data and transform it in such a way so that we can easily separate malignant versus healthy categories and so on and so forth. And yes, in the end, the deep learning model is just separating by a line the two categories once they've been transformed using the filters on the left. So how and what do machine learning models learn? Now, this is really the part which I hope will inspire pathologists to look into machine learning and really start questioning whenever people like myself who are on the computational side approach you and say, hey, I have this great algorithm, it can solve your problems, all of your problems. Because this is really not the case. Machine learning, actually, the current machine learning that we have, such as deep learning, raises many more questions than answers. And obviously, it is great at the certain problems that we're trying to tackle with, but there are also other problems that arise with that we really need to be careful about, particularly in the medical application. So you remember these filters that our convolutional neural network or machine learning model learns? So now let's try to study what these filters are, for example, in medical imaging as well as in other different situations. So these are, again, the filters learned by our model on natural images on a data set called ImageNet, which is 1,000 categories of all sorts of different objects. So when we shuffle the labels, the categories of these images, and we try to learn essentially on the noisy data, on the data that doesn't make any sense, these filters become noise also and don't really make sense for us. So again, we have, for example, an image of a car and a person, a red panda and a bull. But then on the right, we completely shuffle these labels and we're trying to learn a model on this data set. And the features or the filters suddenly do not make any sense at all. They're just noise. Now there was a recent, yes, and while we're learning on this noisy data set of shuffled labels, the model still achieves perfect performance on the training data. It is perfectly able to classify absolute noise. So it means we could perfectly learn the noise or perfectly memorize the data with our deep neural network. So there was an interesting, and this was published in the study called Understanding Deep Learning Requires Rethinking Generalization, which really made people question what do these neural networks do. And in a recent study, Transfusion Understanding Transfer Learning with Applications to Medical Imaging, they've also looked at these filters in terms of two medical imaging data sets. And what they found is that these filters are absolute noise as well. So this really should make us question what are we doing with these models and how reliable they are. And we need to be more careful at designing the tasks that we are trying to solve and question in the first place, does this task make sense to be solved by a machine learning model? So what are the implications of that? In general, when developing a model, we will have training data, we will have validation data, and we'll also have a test data. And this sort of experimental setup, we think, in machine learning, provides us a secure experimental design where we will be certain that once we've trained our model on the training data, validated it on the validation data, and then once again tested it on the test data and it still performs amazing, that we will be fine. And as I've given my example with company X at the start, who've shared their model with a medical student, they were also following this most likely the same approach, expecting that their model will generalize to the data set that that medical student is working with. But however, that is not the case. If you look at it from the perspective of the statistics, you can still make a model that will overfit to the test data and will not generalize to the new data sets. And even if that test data is multi-center and as diverse as possible, if you keep developing the model and testing it on the same test data, it will still overfit most likely to that test data in the end. So let's look at that from the empirical perspective. So this is a study on measuring how hard certain data sets are, how hard certain data sets are within machine learning. So essentially what you need to look at is that the more on the right and the more up the data set is, the harder that data set is for a machine learning algorithm to solve. So you see that red cross on the upper right corner. This is ImageNet. This is the data set that I've mentioned earlier, where you have 1,000 categories and more than 1 million images, which people develop machine learning models to classify. Now, what we suspect, and we currently have master student working on it, is that medical data will be within the range of the CFAR 10 data sets. And ImageNet, what the cross means there is that you couldn't even compute how hard that data set is. It's just way too complicated to even estimate how hard it is. So it is very hard. So you think you're safe by following this approach. Well, there was a study recently published detecting overfitting via adversarial examples, which tries to tackle this exact problem from a more statistical perspective. They try to develop a statistical method which would allow to see if a deep learning model is overfitting to the test set. And what they find is that within this range of medical data, where you have CFAR 10 and CFAR 100 data sets, which have 10 categories and 100 categories, they found that the currently used classification models, convolutional neural networks, which are considered state-of-the-art, they are in fact overfitting to the test data. So this is really something to think about when we are applying these models in medical domain, because we do not have that margin once they are implemented in practice of these models not being able to generalize or performing less or worse than we would expect it. While on the ImageNet, they detected that there is no overfitting of these models. So that's why we really need to have the trade-off between how hard the data is and how complicated is the model that we are using. What other implications does it have for us in terms of the model learning? Now, you will frequently hear that deep learning models or the machine learning models, now artificial intelligence in general, will overcome everyone and will put us all out of jobs and so on and so forth, or that it will lead to new discoveries and so on and so forth. Yes, I absolutely agree with that, and I'm crazy excited about what these machine learnings could do, but let's look at some examples which really also show some other perspective of the whole AI is going to take over topic. So really, let's think back about semantic interpretation of images. The semantic interpretation of images that we may have and the semantic interpretation of images our machine learning model might have. So this is a study published at ACLR Machine Learning Conference this year, but it appeared on the archive last year in 2018. So they've performed a really simple but interesting experiment. So on the left side, we see a texture which would remind us of an elephant. In the middle, we see a cat. And on the right side, we see a cat whose in the texture of that image has been transformed to have the same texture as that of an elephant. And then they take those images and they apply a deep learning model, convolutional neural network, to it. And although by looking at that image on the right, we can see that there is a cat in there, machine learning model cannot see that. It says that it's an Indian elephant. And there are multiple examples that one may come up with where machine learning models fails like that. And that should really make us question whenever we hear that machine learning models are aware of the problem, or they understand how to solve the problem, or that they know better how to solve the problem, or may extract features that we do not know about. It might not necessarily know the features that correspond to the features that we're interested in solving the problem. Now, this is another study published at ACLR this year as well. So what they did in this case, the images on top correspond to the model behavior with respect to a certain input into the model. So images on the bottom are inserted into our model, and they monitor the behavior of the model in terms of how does it respond, what classes does it try to predict, what categories it tries to predict for those images. And those images are meant to simulate what would correspond to a stimulus in human brain to stimulate a certain object or a class. So on the left you have stones, then the second image you have something looking like a monkey, then some sort of plant, a plant again, stairs, and an elephant at the end. So what you can see in this image is that actually the response of machine learning model is absolutely the same to all of these images. Essentially, it does not interpret the images the same way we would do, and therefore that should make us question, again, are the features that machine learning model is extracting meaningful or not? And is it always the case or is it not always the case? And to what extent that is the case? So if you find these topics interesting and relevant, I unfortunately have only 20 minutes for this presentation. We were thinking of, with Catherine, if we could start a newsletter on a rational view on machine learning in medicine and provide examples of what could be done or what is done in terms of research and application in medicine of machine learning models, and try to spark up not also the conversation of what is great about machine learning models, but also provide a healthy dose of skepticism in order to move forward and make these machine learning models as applicable as possible in a practical and clinical setting. Thank you.
Yes, thank you very much, Jeff, for that introduction into machine learning. I would start with one question and afterwards open the questions to the audience. You gave us that nice example with the cat and the elephant, and raising from that, I might ask you, where do you see the current applications or limitations of machine learning, or asking a different question, where do you think that humans are still better in classifying and finding regression models than algorithms are, and where they are not, with regard to pathology, of course?
So first, I can say where the models are worse. So whenever you give a task to the model and the data set to the model, it will try to be as best as it can on this data set with the first possible feature that it will extract from the data set that it will lead to the optimal classification. And that feature might not necessarily be meaningful at all. So what we see with the example of a cat, the model is biased towards textures in ImageNet. And that is not always necessarily what we are looking for. So what does it mean for us is that humans are still much better at interpreting the features that we are looking at. We have much more domain knowledge which could be employed when designing these models and ultimately enforcing on these deep learning models to then making them more robust and more applicable in a practical application, because ultimately the patient will want to know why he's getting a certain diagnosis or not, and we would need to provide an explanation to a patient. And if you have a deep learning model, currently, as it stands in the literature today, there is no way to really interpret what these models are looking at. We can only make empirical studies like the ones I've presented earlier on what these models are doing. But for example, when you try to visualize, what people commonly do, they would visualize filters or activation maps of deep learning models. Well, these actually don't mean anything for us. And another tool within deep learning toolbox, there is attention. And there is a study that shows that actually attention in terms of deep learning is also meaningless and doesn't provide attention to the right features that we would be caring for in certain tasks. Another tool that is commonly used is perturbing the image and then seeing which perturbation leads to the most change in the output, and that way we think this is the area that is most important within an image. And there are certain studies published last year and this year at machine learning conferences which also show that we cannot trust these machine learning or convolutional neural network visualizations in order to understand what are they looking at. So there are multiple, and I think it's up to us to really try to bring that forward and address those issues, because we ultimately care the most about it in the medical domain.
Thank you. Are there any questions from the audience? Over there, please.
Hi, Jeff. Thanks for a nice talk. I was wondering if you have come across the work of Ziegler and Ferguson with Picasso visualization of the neural network layers. They do a deconvolution, and they tend to see, they've proven that, for instance, in a tank application, they were able, it was learning the trees rather than how to find, whether detecting the, the tanks itself. I was wondering if you had gone through that.
Oh, you mean you're referring to an old work from back in the days where they were trying to build a model to detect tanks, and in the end it was finding the trees.
Yeah, but Picasso was able to tell that it was actually detecting the trees, so they were able to fine-tune the model.
Yeah,
to actually,
yeah.
So is it useful? I mean, did you?
I mean, it is useful, and this is what people are trying to do within machine learning. So there was a workshop last year, I think at ICML, where they were discussing unsupervised learning and feature representation learning in general. And the Zubin Gaharmani said there, well, why would you need unsupervised learning for a task for which you know what the ultimate goal is? So the same thing here. For example, if you're trying to learn a model which will show which features are meaningful, then you shouldn't expect that model to learn features that are meaningful. You don't specify it in the loss or anywhere in the optimization. So maybe you should also incorporate that into the loss, just like they did in their work, where they've corrected for the bias, and that way learn the model that you're looking for. So that's what people are starting to do with attention. They will actually learn where to pay attention to as well.
We have one more question.
Every pathologist, before they learn their medical jobs, they go through their infancy and their kids, right? So, and we know that all humans will learn how to interpret the world, at least, when we have no idea what the cell is, and et cetera, et cetera. So can you comment a little bit about the interplay between unsupervised learning, this is basically what infants do, and supervised learning, which is what happens much later in life?
So this is, it's a good question, and I would say it's a big debate in machine learning at this point. So if you look at researchers like Jan LeCun from Facebook, he'll just say, throw loads of data and throw a neural network in it, and it will learn something in the end, whenever in the limit of infinite data. But then you have other people on the other side, like John Tenenbaum from MIT, who works closely with neuroscientists, and they actually show that infants who are learning about the world, they already have a lot of strong priors enforced on their learning, which helps them learn in the most optimal way, which is essentially goes back to the question asked earlier. Maybe even if we do unsupervised learning, we should try to enforce on our model and on our learning something that in the end we're interested in knowing. And essentially, we don't necessarily show what it should learn, but we should direct it towards what it should be learning.
Is there any other question from audience? Well, I have one question for you, Jeff. Machine learning and deep learning, are these both interchangeable terms, or they have a different meaning?
To me, it's all statistics. Deep learning is just what they started saying for neural networks that are very deep, and that's as far as it gets. It's just deep neural networks, but you can use them in, well, you can't use interchangeable. Deep learning would be just everything that has a deep neural network in it, and then machine learning will be, and machine learning itself is a very vast literature of many, many other models that are also very powerful and strong, and could do loads of useful things as well. In fact, there is a big trend now, if you look at researchers at Google and DeepMind who work on combining classical machine learning algorithms with deep learning. Essentially, you can take any probabilistic model and you parameterize it with neural network, and suddenly you can enforce that structure that we've talked about on a neural network.